Previously, we discussed about Knapp algorithm of pattern matching. Today, our topic is Knuth-Morris-Pratt algorithm. There was actually a problem in Knapp algorithm, which is after getting a pattern in the text, uh, it uh, it was checked every position of the text, which was quite unnecessary. So, in Knuth-Morris-Pratt algorithm, the limitations of Knapp algorithm will be solved. Now see what is Knuth-Morris-Pratt algorithm and how it works. Before we proceed to the algorithm, we have to know about the prefix and suffix of a string. Suppose there is a string S, it contains the text AABCAB. So what will be the prefix if we consider from the first character to last character, we can make a lot of subset of the string S. Suppose A is a subset of S double A. So this 2A is also a prefix or subset of A. AAB is also a prefix of S. AABC, AABCA, and finally AABCAB. This is the subset of string S or prefix of string S. What is called prefix? Because we consider from the first to last character for scanning. If we scan the text from last character to first character, that time it will call suffix. So what will be the suffix of string S? First one is V, the last character, then last two character. AB can also be a suffix. CAB can also be a suffix. So next suffix will be BCAB, then ABCAB, and finally AABCAB. Okay. Now go to the algorithm. So there are actually two steps in the algorithm. First one is we have to create a longest prefix suffix subarray, and we have to pre-process the pattern. After pre-processing that pattern, we will use that pattern or we will use the LPS array to search the pattern in the text efficiently. And it will skip unnecessary comparisons on mismatches. Okay, suppose the given text is ABABA and the pattern is ABA. So at first we have to create the LPS for the pattern P. So text T will not consider it fast. At first we have to create pattern P. Let's go. Suppose this is a pattern. Text T is there and pattern is ABA. So we have to create the LPS array. So initially, the length of the pattern P, which is M, is equal to 3, since there are 3 characters, ABA. And we consider I equal to 1, the second character of the pattern, and len is equal to 0. So len is equal to 0. That means initially we have 0 length of a longest prefix suffix. There is actually, before scanning of the pattern, we got 0 length of longest prefix suffix array. So initial position of the LPS array should contain 0 always. Okay. Now proceed to the scanning portion. How many times it will scanning? It will scan through m-1 position. I equal to 1 to m-1 position, it will scan. So initially, when I equal to 1, len is equal to 0, LPS is equal to 0. Now, we will compare the PLAN and PI. If there is a mismatch, that time len will be 0 and LPS, the value of the new LPS will be 0. But I will be incremented by 1, which is 2. So now go to the next characteristic, which is Pi is equal to A. Since the land value is equal to 0, okay, and Pi is equal to A. So Pi and Pland matches here. If there is a match, then increase the value of land, which is 1, and saves it to the LPS array. So it saves for the 1 position, for the 2 position, for the I is equal to 2 position is 1. So finally, we got the LPS array. And since the value of I is equal to 3, which is actually not less than m, and that is false. If that is false, then I will exit from the loop. And finally, we got the array, LPS array, 0, 0, 1 for the pattern ABA. It means we got 0 length of suffix, sorry, 0 length of prefix in the 0 position, 0 length of prefix in the 1th position, but 1 length of prefix in the position 2. Okay, now we use this LPS array to search the pattern in the text T. Okay, start. Initially, the value of n is the length of T, which denotes the value of n, which is 5, and the value of m is equal to 3. Value of m means the length of the pattern P. Initially, both the indicator value I and j is equal to 0. So starting, I represents actually the text position, and the pattern P position denotes the value of j. So if there is a match between Pj and Ti, if there is a match between Pj and Ti, that time the value of I and j both will be increased. The value of I and j both will be increased. But in the naive algorithm, we didn't see that. So this is the improvement in the KMP algorithm. So when the matches occur, we will proceed to the next position in pattern P and the next position in pattern in text T. Okay. So there is also matches present in that I equal to 1 position for the text T and j equal to 1th position of the pattern P. That means Pj is equal to Ti. If there is a match, go to the next position of T and P. That means value of I and j will be increased, and which is 2. Okay, now there is also matches present in Ti and in Pj. If there is a match, we will increase the value of I and j. Value of I is equal to 3 and value of j is equal to 3. Here we see that the value of j is equal to value of m, which means we will get the pattern. So we will get the pattern for which position? We will get the pattern in the position I minus j. That means 3 minus 3 is equal to 0th position. So in the 0th position, we get the pattern. And the value of j will be updated by LPS j minus 1. LPS j minus 1 means LPS 2. So what is there in the LPS 2 is, which is 1. So new value of j will be 1. Okay. Now, to that, we see that the value of I is equal to 3 here. It will be 3 here. And the value of j is equal to 1. So we see that there is a match between T, I, and Pj. Since there is a matching in T, I, and Pj, we will increase both the value of I and j, which is I will be incremented by 1, which is 4, and j is incremented by 1, which is 2. Now, here we see that there is also a match in the position I equal to 4 and then in the position j equal to 2. So when we compare Ti and Pj, we see that there is a match. If there is a match, just increase the value of I and increase the value of j. So I is equal to 5 and j is equal to 3. Since there is a value updated by j is equal to 3, which is equal to length of the pattern P. That means value of j and m is equal. So we can tell that we got the pattern again, and the pattern is found at I minus j position, which is number 2 position. Number 2 position, we will get that pattern. And the j will be updated by LPS j minus 1. That means j is updated in LPS 2, which is 1. So the value of j will be 1 here. Now, since I is equal to 5 and our loop, there is a loop for the I, which I is less than n is false because the value of I and n is getting equal. That means it will come out from the loop and search is completed. So finally, we can say that the pattern found at I equal to 0 and I equal to 2 position. So we see that actually in KMP algorithm, it will not check every position of the text T. But in the naive algorithm, it was.